Right, let's go. So, the idea here is that we want to implement an ADT to represent stacks. Now, we just saw how stacks were useful in the implementation of C in the runtime, but stacks are generally useful in other contexts as well. So, stacks have two characteristic operations, push and pop. Push adds an element onto the top of the stack, so if I start with an empty stack and push 5, then I've got a stack 5 on the top. If I then push 3, I've got 3 on top of 5, push 6, I've got 6 on top of 3, push 1, I've got 1 on top of 6. And the thing about stacks is you can only take the thing off the top. So if you think about a stack of plates, if you pull the one out from the middle, the whole stack falls over, and you end up with a lot of broken plates. So, pushing 1, then when you pop, 1 comes off the stack. If you pop again, the current top element, 6, comes off the stack. You can then push again, you put another element on the stack, push another element, pop. Then you can go pop, pop, pop. If you try to pop an empty stack, that's an error. There's never really a problem pushing onto a stack unless you implement the stack in a way that kind of looks like we've got here. This looks like an array, and we're simply putting values into the elements of the array. Now, at some point, we need to decide how big that array is. And let's say we say 10. So we've got space to push 10 elements onto the stack. What happens if we push 11? Oh dear. Well, we could have made the array 100. What happens if we try to push 101? So it doesn't matter what size array, eventually you're going to bump in and overflow the array. So implementing stacks using an array, fine, it's simple, but there is the potential for runtime errors that you don't really want. So we decided to use a data structure that's more flexible than that, and the data structure can just grow as large as you need it to grow and can shrink down again when you're not using it. So, let me see. So these are the operations. We're going to implement all of these operations. Some of them are already implemented, I think, in the file. But before that, no, not before that. Before that, let's, one thing we need to, and by the way, you go and poke around in the 1521 class account. If you go tilde CS1521 public HTML 17S2 lex, LECS for lectures, you'll find a directory that looks kind of like this. And then if you go down into something like we go to, then you'll find a whole lot of slides, but you will also find a directory called exercises, which contains all of the programming stuff that I happen to do in the class. And if we go into stack, we'll find our stack ADT. So here's the interface to the stack. It's pretty much the same as what was on that slide. Make a stack. So create a new empty stack, returns a reference to that stack. Remember that a stack is actually defined as a pointer to a stack representation. And the stack representation is something that users of the stack type can't see. And we don't want them to see it because they might start poking around inside the structures themselves. What we want users or clients to see of this data type is simply these function interfaces. So they can create an empty stack, they can free it, they can push stuff onto it, they can pop stuff off it, and they can do these various other kinds of checks. So that's what a user sees. They see that there's a data type stack, capital S-T-A-C-K, that one there, and they see a bunch of functions that operate on those stacks. As an implementer, we have to build stack.c. So we have to come up with a representation for the data structure. So down here you can see that our stack representation is going to be a counter for the number of items in the stack, and there's going to be a pointer to a list of items. The items in the list are represented by stack nodes, where each stack node contains a value and a pointer to the next stack node. Alright, so always with these pointer things, it's probably easy to have a look at diagrams, so I'm going to try and do something with my drawing program. Alright, so we've got a stack. This is the initial representation of the stack. We create a stack rep object, and we'd say there are currently no items. Remember that the items thing is a pointer. The standard way of saying there is no pointer is to have a value of null, and there are 0 items in the stack. So if we go and look at the makeStack function, basically that's what that would do. It would malloc a stack rep and then set those values inside the new stack rep object. Alright, so we create our initially empty stack, and then we go push. Want to do that? We push 5. Alright, so the way this linked list is going to work, it's going to create a new stack node. Up here using malloc. So this object here is an object of type stack node. This object here is an object of type stack rep. They look like kind of similar kinds of structures. They've each got an integer and a pointer, but they're different kinds of objects. All right, into this object, we're going to put the value that we just pushed. So the value 5 goes there. This object, remember that the second part of a stack node is a pointer to the next node. Well, there's only one node in the stack, so there's no pointer to any next node, so we can leave that as null. Well, I think I might need to grab a little pointer that I can use. The other thing that we need to do is, now this node that we just created is the first node in the stack, and therefore we have to set up the stack representation so that its items value points to that node. So it's no longer going to be null. What we're actually going to have is, a pointer that goes from here, get in there, to here. So having done push 5, that's the result we want to end up with, and what I showed you with updating the diagram is pretty much what the program has to do. Let's have a look at pushing 7. Now, the way we're going to represent our stack is that the top of the stack is always going to be the first item in the items list. So we're just pushing things, so we're pushing new values in front of the existing values. So pushing 7, once again, push basically means create a new object, create it up here, put the value 7 into it, so that's pretty straightforward. And now what has to happen is this new object is going to be the first object in the list. So this pointer here is now going to point down to this object. This object conceptually is going to move a bit to the right. Let's go with it. And this object that we've just created here now has to point to that object. Now if you look at the way I just did this, I've actually lost the pointer to this object, because the only pointer to that object that I had was that one there. So let's put it back. So that's what the original stack looked like. What is that little thing doing? Go away. This is the new object that I've created. So what I need to do is, rather than this being null, I need to get rid of that. I need to make it into a pointer. Stop that. Let's see if this works. Where did that go? I put it down there. Alright, good. So, this pointer here needs to point to this object here. So basically I'm going to take a copy of that pointer value and I'm going to make this object here point to that object. Okay, so I haven't lost a reference to any object yet. And then the next thing that I need to do is I need to change this so that it now points to this object. So that's how I want to change things when I push a new object. Right, let's just move all this stuff across a bit. Move all of this stuff across a bit. Alright, the next thing we're going to do, we're going to push 2. So it's going to be the same kind of strategy. When we push, we always create a new node. So here's our new node. Since we're pushing 2, we store the value 2 into that node. We then want to make this new node the first node in the list. Before we do that, we need to grab a copy of this pointer and store that in this object. So we assign that. And the final thing that we need to do, this node needs to become the first node in the list. And so we redirect this pointer rather than pointing here. Let go. You filthy swine, what are you doing there? It's going to drive me mad. Alright. Where is it? Go away. Let me set that up again. Right, I've got 2 separate points. So the ultimate goal is that the items thing points here, and this item here points to this item here. Okay, so hopefully you're starting to see the pattern of how we go about doing this. Push means create a new stack node, link it to the node that's currently at the start of the list. That becomes the next node for this new stack node, and then this new stack node becomes the first node in the list. So all we're going to do is write that in C. Next operation on our list is a pop. What is it? Thank you. What does a pop have to do? What a pop has to do is remove the item from the front of the list. It also actually has to make a copy of the value, and that's something that we return. But I'm more interested in the way we modify the structure of the list. So, what has to happen here is this object is going to be removed, but before removing it, we need to say that's no longer the item at the start of the list. This is the new first item in the list. Okay, and obviously the way we can do that is by making a copy of that into there. This pointer still exists, but it doesn't matter, it's not really relevant. And so the next thing to do is free that object. And now we've ended up with the new state of the list. Okay? So, I don't know how much that helped. I hope it helped a little bit. So let's take a look at how we might do that in C code. Right, so here I've done the make stack function. So we malloc a new stack representation object, and we initialize it to the items to null because we don't have a linked list, and we initialize the counter of items to 0. Alright, so when we come to doing a push stack, remember back to the diagram, the first thing we do is we malloc a stack node object. Actually, we've got a data type called stack node. So to do that, we're going to need a pointer variable, and then we can say create AO lock. So we create a new stack node. That object currently doesn't have any values stored inside it. One of its components is value, I think. Let me just check that. It's called val. So the value that's stored in that stack node is the thing that we're pushing, and so that I've probably unfortunately called item. Right. Since we're pushing, I'll let that. Okay, so that's the thing that fills in the number 2 or the digit 2 or whatever in the new stack node. So that was when so what we've just done is effectively this. So we've created one of these and we've stored the value, the item value into it. Next thing to do. We need to set the next pointer. So if you remember back to the diagram, what we effectively do is we make a copy of this pointer and make the pointer value of the new stack node point to that. Okay, so the way to do that in C remember that's the next component of the new stack node item, and the thing that we want to point it to is a copy of the current pointer to the first item in the list, and we can get that from there. Okay, so I've just done making a copy of that into there. The other thing that needs to happen is that this new object needs to become the first item in the list. So we need to change the value of this pointer to point to that. So we just took a copy of S items, so now we need to make S items point to new. And having done that, we've made all of the transformations to the data structure that we needed to in order to achieve this state here. Now, one thing to notice about that, what happens if we're pushing onto an initially empty stack? The initial value of items in an empty stack is null. Okay? So the first time we push a new stack node onto the stack, we're going to set the value of its next pointer to be equal to null, which is the initial value of S arrow item. By the way, does everyone understand that notation before I'm standing here talking about stuff and everyone's thinking, what the hell is that?
I don't want to.
Is that alright? This is a pointer to a structure. This arrow dereferences the pointer and then it allows us to access a field in the structure being pointed to. Alright, so that's how we implement push. And I should point out, the way we're implementing this stack is absolutely the simplest way that you can do it. If you wanted to, you could change the implementation so it put the new item at the end of the list. That's more complicated. This is really simple. Okay, so speaking of really simple, if we want to pop 2, then this node is going to go away, and this node is going to become the new node at the start of the list. And basically what that means is that we need to redirect this pointer, rather than pointing here, it points to there. Okay, in terms of the data structures, that's basically just saying this S arrow items is equal to this object next. Right? This object was the item at the start of the list. Now, if we make that assignment there, do we have any pointers that are referring to this object? No, so we've lost it. So what we need to do before doing that assignment is probably have another pointer and make a copy of that pointer. So we copy that pointer down to here. So at least we've still got a reference to this object. We can call that old or something. Okay? So when we do this assignment, we haven't lost our one and only pointer to this object, but we've still redirected the item listing. So, having done that, we can then get rid of that object. So we can do that. So, rendering that in C, it's basically just a matter of having somewhere to remember the old pointer value. Oh, I forgot something. What did I forget in push? How come it didn't yell at me? I've added a new item, so I better increment my item count. Okay, so we come down here. Alright, I'll keep going with this. Okay, so we've grabbed a pointer to the first node in the list, current first node in the list. We now want to bypass that node. So the way we're going to do that, we're going to say that the new first node in the list, the first node in the list is denoted by S arrow items, is equal to the node after the node that we just removed. In other words, it's equal to old arrow next. Okay, so that's just achieved the effect of that bypass there. Alright, what else do we need to do? We need to free up old. But another trick, alright, I'll show you a potential problem. We free up old. And remember that one of the points of pop is that it returns the value that used to be on the top of the stack. If we freed up old, where's the value that was on the top of the stack? It's gone. So another thing that we need to remember before taking an action like this is to grab a copy of the value. I'll just call it val equals. So we had to grab a copy of the pointer to this object before we did a redirection. redirect of the pointers, and we had to grab a copy of the value that was stored in that node before we released the memory that the node was using. And then finally, the last thing that we need to do, or the second last thing we need to do, is to return the value. But before doing that, the other thing that we need to do is to decrement the counter for the number of items in the stack. Okay? So grab a copy of a pointer to that old object that we're about to delete, and we're about to lose the only pointer reference to it, which is that value there. We then redirect that pointer for the head of the stack, or the top of the stack, to this node here, and then we grab a copy of the value out of this node, then we remove that node. Alright.
What if the stack's empty?
Ah, good point. Thank you. Well, we could take the cheap and nasty approach, and we could say, that'd be one simple solution. But assert, yeah, it's a very crude way of handling errors, I would argue. Probably, I mean, it's going to give an error message that says something like, that assertion was violated. Now for a user of the stack object, that's not particularly helpful. But, I mean, this raises a whole issue about the way C handles error conditions. A lot of other languages have a notion of exceptions that you can use to trap errors and handle them in a slightly sensible way. In C, you can recognise that the error has occurred, but you can't kind of escape from the normal control flow. So you're going to have to return something. And then the question is, well, what value can I return if I tried to pop from an empty stack? One thing you could certainly do is, rather than doing the assert, you could actually check that condition. Print out some kind of error message, but I mean that's if someone's written a program that uses stacks, they probably don't want that to be spewing out at them either. And then return what? Any value that we return, in theory, is a legitimate return value. So you couldn't recognise, the user couldn't recognise that something had gone wrong, apart from the appearance of an error message on their screen. If we had a scenario where we were dealing with, say, just positive integers, in fact these stacks actually are stacks of characters. So in theory we could pick a character that's not likely to be useful on the stack, and we could return that value. But if we were dealing with stacks of numbers, or if, in particular if we were dealing with stacks of positive integers, then we could return a value that wasn't a legitimate return value, and it would then be up to the user to do something about it. So we could return an error value like -1. So then, every time the user used the pop function, they'd have to check whether return value was legitimate or whether it was -1. And that's kind of analogous to what we normally do with malloc, where we try to do the malloc and then we check whether it was successful. And if it wasn't successful, then we quit the program. So malloc doesn't have a nice way of handling errors either. all it can do is return null if it can't allocate new space. And then a user of malloc can check that. And I guess I should have done, where else did I do? No, good. I don't know, so does that answer the question? Not really. I mean, it answers as well as you can answer it for C. So you could either use assert, that'll kill a program, which is a bit brutal, or you can do something like that. And if you've got a possible distinguished value that's recognisable as different from any valid return value, then you can try and use that as well. Alright, so that's how we could hop node. We never have to particularly worry about push. The only issue is that maybe we pushed so many values that the heap has grown gigantic and it's bumped into the stack, in which case malloc would fail. So we can't push anything else onto the stack. But we've already, I just added a check for that situation occurring, and at that point we just give up. Alright, is it an empty stack? Now these ones become really easy. How do we recognise an empty stack? Yeah, that's one way. There's two ways we can recognise it. Or we can use that counter that we've been carefully maintaining. So you could use one of them or the other. You obviously don't use both. That's not a legitimate C function, clearly. Size of the stack, that's pretty straightforward. It's basically a count of the number of items. Free a stack, alright? That's slightly more interesting. When we're freeing a stack, let's say we do a free stack of this thing, okay? Clearly, we want to remove all of these objects. We obviously want to remove the stack representation because in some sense, that is the stack. But we also want to remove any lingering stack nodes that may exist. Okay. So, that's an interesting one. So, removing all the stack nodes, there's a couple of ways you can do it. One way is to have a pointer object. Let me just remove that. That starts out pointing here, and then we could free that and move on to the next one. Actually, before doing that, I think I'll do the printing of the stack, because that kind of leads into that. So if we want to print a stack, similar kind of deal. We want to start from the front. We want to print the value that's stored in that node. Then we want to print the value that's stored in that node. And having done that, we need to recognise that we've reached the end of the stack. Okay? So a standard technique for doing that is to have a stack node pointer that references the current node. Okay? Now the current node initially starts out pointing at the first node in the stack, and S items always gives us a pointer to the first node in the stack. Right, think of the simplest case where there's nothing to print because the stack's empty. The first thing we're going to see is that the initial value of current is null. If the list isn't empty, then current is initially going to point here. So when we said current is assigned S items, that's making a copy of that pointed to here, so it's pointing to the same object. And we want to print out the value 7. Having done that, we need to move to the next item in the list. So current has to advance by 1 position, basically by being assigned that particular value. And if we keep doing that, eventually we're going to get to the point where current is assigned the value null, and we know that we've reached the end of the list. So always we can recognise the end of the list by the fact that our current pointer is equal to null. So while the current pointer isn't equal to null, it means we've got something else that needs to be printed out. Alright, so what we want to do, we want to print out the value that's stored in the current node. Alright, so that would be done. Value in the current node we can access like that. Okay, and print it out. Now the other thing that we have to do at this point, current has to move to the next node. And the classic maneuver in playing with lists is to advance the current pointer like that. So, this is kind of the I++ of linked lists. So you move current from the current node to the next node. And then you're going to move it to the next node and the next node, and eventually the value of next is going to be equal to null. Current will be assigned the value null, and then we know that the loop can terminate. And that's pretty much it. So that will print out a list of all the items in the stack from top to bottom. Now one thing that we might want to do, we might want to tell the user where the top is. And we might want to add a new line character at the end of the printout. So we could do that, and I reckon that would be a reasonable implementation of show stack. Okay, so let's just, for free stack, we know that we have to do something like this. We need to start at the start of the list, and we need to move along the nodes, and we need to delete each node as we go. Now, if the current node is not equal to null, it means that we want to delete that node. But as soon as we do that free, we pretend we've lost that node. And so, how can we do that? So before we delete the current node, we need to remember where the next node is. And that's easy enough. It's kind of, we had a similar kind of issue in the previous. So the first thing we do is we grab a copy of the next pointer, and then we can use that later on. So rather than being the simple current equals current next, we need to assign the next pointer then delete the current node, and then advance to the next node using the saved pointer value that we had before. Right, that's almost done, but remember all that that's going to do is delete that and delete that, but we've still got this thing. Okay, so the final thing that we need to do, we simply need to delete that stack rep, the stack rep object. And that thing is the object called S. It's the object being pointed to by the thing called S. So that's the complete implementation of freeing the stack. Alright, so that's basic linked list manipulation. So if you can understand how that all works, hopefully you can understand the more complicated types of linked lists. Any questions on that? Yeah.
How do you check if you have memory limitations with that one?
Use Valgrind. Oh, I don't use it. I never have memory lists. Really? You haven't had instruction on using Valgrind? Interesting. We should make some videos then. By the way, have you all seen there's a bunch of videos that we made that will help with various aspects of, it was actually designed for COMP1521, but there's certainly a description of, so it's a playlist and you can see there's a thing about stacks, there's a thing about malloc and free, so you might want to take a look at that as well. Right, that'll do for today.